We have seen the functioning of PIN diode and also how we can make switches, phase shifters using PIN diode. Let us start a new topic, Schottky diodes and detectors. PN junction diodes, which are used at low frequencies, have large junction capacitance, and this makes such diodes unsuitable for microwave frequencies. Schottky diodes have semiconductor metal junction, and this results in a much lower junction capacitance. Usually, in the design of Schottky diodes, N-type gallium arsenide is used, and for lower frequency operation, N-type silicon is also used. Let us see how this device is modeled mathematically. So, the current I flowing through a Schottky diode can be written as Is e to the power alpha v minus 1, where this alpha is equal to q by n k t. N is the ideality factor. For Schottky diodes, it is approximately 1.05. K is the Boltzmann's constant. T is absolute temperature in degree Kelvin, and Q is the electronic charge. Is is the saturation current, and it is very small. So, this is the device is modeled same as conventional diode, and we can see that when V is a large reverse voltage, that means e to the power minus alpha v is very small, then we will have I equal to minus of Is, the reverse saturation current. Now, this diode, since it has a lower capacitance because of the metal semiconductor junction, it has very fast response, and because of this faster response, this diode is used for signal detection. So, before we go for signal detection, let us see the small signal approximation that is used to describe the behavior of such diode. So, let this voltage V consist of two parts, V naught, which is the DC bias voltage, and small v, this is the AC component of the voltage. Usually any signal variation that is present. Now, what we can do, we can go for Taylor series expansion for this current I V around this DC voltage V naught. So, once this expansion is carried out, I v can be written as I naught. I naught is the current when V equal to V naught plus small v di dv at V equal to V naught plus half small v square d square I dv square at V equal to V naught. There will be higher order terms which are neglected, and we approximate I v by these three terms. Now, given I v equal to I s e to the power alpha v minus 1, therefore, I naught, which is I v naught, is I s e to the power alpha v naught minus 1, and if you take the first derivative di dv at V naught is alpha I s e to the power alpha V naught, and this can be written as, here we can see that I s e to the power alpha V naught is essentially I naught plus I s, and therefore, we can write this to be alpha I naught plus I s, and this is written as G d, and which can be written as 1 by R j. Now, here this G d, it is the dynamic conductance of the diode, because this is a ratio d I by d v. So, G d is the dynamic conductance and R j is the junction resistance, and this is reciprocal of the junction resistance. Let us now evaluate the second derivative. D square I dv square at V equal to V naught is alpha square I s e to the power alpha V naught. Now, as before, we can write, we can substitute I s e to the power alpha V naught by I naught plus I s. So, it becomes alpha square I naught plus I s, which is alpha into G d, and this is represented as G d dash, and therefore, now we can have the diode current I v approximated as I naught V G d plus half V square G d dash. Now, as we said, we will use these Schottky diodes for signal detection, because it has very fast response, and in such detector application the nonlinearity of the diode is used to demodulate an amplitude modulated RF carrier. Now, when we are performing demodulation operation, the voltage signal that is applied to the diode can be written as Vt is equal to V naught 1 plus m cos omega mt cos omega Ct. Here omega m is the frequency of the modulating signal, omega c is the carrier frequency, and m is the modulation index. We have omega m very small compared to omega c, and also modulation index m is less than 1. Please note that here we are considering a single tone modulation. Now, when this voltage is applied to the diode, since IV is given by I naught V GD plus half V square GD dash, we can therefore write IT is equal to GD V naught 1 plus m cos omega mt cos omega Ct plus half V naught square GD dash 1 plus m cos omega mt square cos square omega Ct. Once we have this current, please note that it is the AC part of the current, essentially IV minus I naught, and we can actually get the spectrum for this current, and it will have different frequency components. It will have frequency components omega m, 2 omega m, omega m plus omega c, omega c minus omega m, then 2 omega c, like that. We want to detect our modulating signal which has a frequency omega m. So, in order to detect this signal, we pass this IT through a low pass filter. So, after low pass filtering of the output and removal of the DC component, we can write I naught t is equal to V naught square GD dash by 2 m cos omega mt. So, we find that the AC current signal at the detector output, it is proportional to the square of the signal voltage V naught, and therefore, this current at the detector output is proportional to the input power. We should note that this square law behavior of this type of Schottky diodes is obtained over a limited range of input power. So, over that limited range of input power, this diode can be used as a detector for modulated microwave signals. So, we have discussed in brief the operation of the Schottky diode and how it can be used as a detector Let us now consider another device which is a tunnel diode. A tunnel diode is a p-n junction, and the difference between normal diode is that the p and n regions are highly doped. The doping concentration of the order of 10 to the power 19 to 10 to the power 20. Such doping profile allows electron tunneling through a narrow energy band gap, leading to negative resistance at high frequencies. This type of diodes are also called Schottky diodes. Schottky invented the diodes operating on this principle of tunneling. Tunnel diodes can be used for oscillators as well as amplifiers. And before high frequency transistors became available, tunnel diodes provided a means of high frequency amplification. Tunnel diodes provided a mean of high frequency amplification with a solid state device. Such amplifier employs the diode in a one port reflection circuit, where the negative RF resistance of the device produces a reflection coefficient having magnitude greater than unity, and therefore provides amplification of an incident signal. Let us see the features of tunnel diode. They are low cost, lightweight, high speed, low power operation, low noise, and high peak current to valley current ratio we will see. Now, this diagram shows the IV characteristic of a tunnel diode. So, here this point is the peak current. We can see that initially, as we increase the applied voltage across the diode, the forward current increases, then it reaches a peak value, and then with the increase of voltage, the current actually decreases, and this decrease of current continues till some voltage which is shown as Vv here. So, Vp is the voltage corresponding to peak current Ip, and this is the lowest current which is called the valley current, and Vv is the voltage corresponding to the valley current. And then beyond this voltage, if the applied voltage is increased, then the diode operates or functions as an ordinary diode with the current increasing exponentially with the rise of voltage. Now, this region is the negative resistance region, which is very important for amplification of signals as well as for designing oscillators using tunnel diodes. Let us now try to understand tunnel diode operation qualitatively. Here we can see that we have a p-n junction, and as we have mentioned that both p and n region, they are highly doped, and because of this heavy doping we have empty states above the Fermi level in the p side, and we have field states below the Fermi level in the n side. When no bias is applied, the Fermi level is same in both p and n type material. This difference may be noted because in ordinary p-n junction diode, Fermi level it lies in the forbidden region. Now, here V 0 is the barrier voltage and E g it is the forbidden band gap. So, we have already discussed tunnel diode has heavily doped p-n junction. For a tunnel diode, Fermi level is inside the valence band in p type and inside conduction band in n type. Now, for tunneling action, the depletion region should be very thin. This is the depletion region. When the junction is formed, we have the depletion region around the junction of p and n type material, and there must be field states on one side. So, here we have field states in the n type material and allowable vacant states on the other side. So, if such a condition exists, then the electrons can move from this or tunnel through the p type material. Whenever a bias is applied, the electrons from these field states will tunnel to fill the empty states in the p type material. So, let us try to illustrate this situation. So, here we can see that when a small bias voltage is applied, that means V is between 0 to V p. Now, we will have the barrier height reduced as compared to V naught, and therefore, we will have this field states energy wise, these field states in the conduction band aligning partially with the vacant states in the p type material, and electrons can now move directly from these field states to the vacant states in p type material through the tunneling process. and when such movement of electrons takes place, this will result in a small current flowing in the device. It is interesting to note that under zero bias condition, there was no overlap. As we increase the bias voltage, this alignment of the field state in conduction band and vacant states in the valence band, this will increase. So, when the tunnel diode is forward biased by a voltage V which is greater than 0, but less than V p, the potential barrier is reduced by the magnitude of the applied forward voltage. A difference in Fermi level is created. Since there are field states in the conduction band and empty states in the valence band, electrons tunnel through the barrier from N to P, giving rise to forward tunneling current. Now, as we keep on increasing this applied voltage V, a situation will come when this field band in the conduction band, when this field bands in the N type material will perfectly align with the empty states in the P type material, and we will have maximum number of electrons tunneling from N side to P side. And when V is equal to V p, that is why we get the maximum current or the peak current I p. So, this red line is representing the current component that is being contributed by the tunneling mechanism, and we can see that at V equal to V p, we have I reaching the peak current I p. So, we have maximum number of electrons now can tunnel from N side to P side, and the diode current attains its maximum value I p. As we continue increasing the applied voltage V, now we can see that the overlap region between the empty states in P and field states in N, it gradually reduces, and this reduction results in a decrease in the current, as now less number of electrons are available to tunnel from N to P region. So, we see that this is the part from V p to V b, the voltage increases, but the current actually decreases, and as we keep on increasing the voltage for very large bias voltage, finally the tunneling current will become 0. As I have mentioned, there are two components of current here. This one is the current component because of the tunneling, and this is normal diode operation, the injection current. So, when we increase the applied voltage V beyond V B, now there is no overlap between these empty and filled states, and from here onward the electrons, they will have to move over this potential barrier if these electrons are to migrate to the p region, and therefore, the normal carrier injection mechanism starts taking place, and therefore, the tunneling of electrons actually takes place over certain range of applied voltages, and this phenomena will happen only when the p and n sides, they are very heavily doped, favoring a situation where direct tunneling of electrons can take place. So, when this V is greater than V V, we find that here now the tunnel current, the current due to tunnel effect decreases and normal injection current starts increasing. So, when V becomes greater than V V, ordinary injection current at p n junction starts to flow. The total current is the sum of the tunneling and injection current, and I V is the minimum value of the current at applied voltage V V. This is also the valley current and this is the peak current. It may be noted that in this part the current increases with the voltage. So, here in this region and also in this region we have the positive resistance region of operation of the diode, whereas from V p to V B this region provides the negative resistance region of operation. Now, let us consider in the negative resistance region a point B where the voltage is given by V B. Then the negative conductance at this point is given by minus G is equal to d I by d V, that means the change in current divided by the change in voltage at the point B V, and this can also be written as minus 1 by R n, where R n is the magnitude of the negative resistance. Please note that this G or R n, they will remain constant only over a small region, because if I take another point here and calculate G, the slope will be different. So, only for small changes in voltage this value of G will remain constant, otherwise it will keep changing as we move from V p to V b. In this region, the tunnel diode is also modeled as a negative resistance and a capacitance C representing the capacitance of the junction. There are of course other parasitic parameters are there, the packaging capacitance, the inductance of the connecting lead, these are not shown here, and this is the simplified equivalent circuit model of a tunnel diode. Let us now see how we can have amplification or oscillation from this type of tunnel diodes. Here we see the amplification with a tunnel diode when a load resistance R L is loaded with a tunnel diode in a parallel manner. Now, given that P out is equal to V square by R L, and if A is the tunnel diode gain, and then we can write P in to be V square by R L into A, and also this being a negative resistance device, it will generate power. A positive resistance, it absorbs or dissipate power, whereas a negative resistance device, it will supply or generate power. So, that is given by V square by R n, because it is a parallel connection. So, V is common for the load as well as for the tunnel diode, and from there equating V square by A R L plus V square by R n equal to V square by R L, we can find out A to be equal to R n by R L minus R n. So, we can see that if R L becomes equal to R n, load resistance approaches the resistance of the negative resistance of the tunnel diode. In that case, A tends to infinity and the device goes into oscillation. So, in brief, we have seen the operation of a tunnel diode, how it provides a negative resistance region, and how this negative resistance region can be utilized for amplification or for certain load conditions. The device may give rise to oscillations as well. In the next topic, we will consider a gun diode, which is called a transferred electron device.